Okay, good afternoon, everybody. So thank you very much for attending a new CASS talk organized by IEEE Sequencing Systems Society Rio Grande do Sul chapter in cooperation with the Federal University of Rio Grande do Sul. So it's a great pleasure to have here today Professor Keshab Parhi from University of Minnesota, that is IEEE Sequencing System Distinguished Lecturer. So today he's going to talk about hardware security, and also if you wanted to see a second talk of Professor Parhi, as he is IEEE CASS Distinguished Lecturer, there is also a recorded talk that is available going through the CASS, the main CASS Keshab. So Professor Keshab received the bachelor degree from the Indian Institute of Technology in '82, and the master degree from the University of Pennsylvania, and the PhD degree from University of California in Berkeley. So since '88, he has been with the University of Minnesota as a professor, where he is currently Distinguished McKnight University Professor and Edgar Johnson Professor in the Department of Electrical and Computer Engineering. He has published over 650 papers, has authored the textbook of VLSI Digital Signal Processing System by Willey in '99, and he also co-edited the reference book Digital Signal Processing for Multimedia Systems by Marcel Decker in '99. Professor Parhi is widely recognized for his work on high-level transformations of iterative data flow computations and for his research on hardware accelerators for signal processing and network system. And his current research addresses VLSI accelerators for signal processing and machine learning, including deep learning, data-driven neuroscience, hardware security, and molecular computing. And Dr. Parhi receives numerous awards, including the 2003 IEEE Tomiyasu Technical Field Award, the 2017 Mac van Valkenburg Award, the 2012 Charles Desor Technical Achievement Award, and in '99 the Golden Jubilee Medal from the IEEE Sequencing Systems Society, and in 2004 the F. Thurman Award from the American Society of Engineering Education. He served as the editor-in-chief of the IEEE Transactions on Sequencing System Part 1. And he is a distinguished lecturer of IEEE Sequencing System Society during '96 and '98, and again 2019 to 2021. And he was elected member of the Board of Governors of IEEE Sequencing System Society from 2005 to 2007, and he is fellow of IEEE since '96, and also of AAS 2017. So this is just a short CV, so that is very impressive. So thank you very much again, Professor Parhi, to accept our invitation to talk today about hardware security. So now I will put your slides and give you the control of the presentation to start your talk. So thank you very much. Now you have the control of the slides.
Okay. Well, thank you, Ricardo, for asking me to be part of your series of talks, interesting talks and exciting talks. So I still don't see the slide control now. Maybe.
Sorry, it was my fault here. Okay, now you have.
Yeah, I see it now. Thank you. Yeah, well, it's really my pleasure. Good afternoon in Brazil, and good morning or good evening wherever you are. These types of virtual talks organized by Ricardo are, I think, a great blessing not only for Brazil but also for all the members of our Circuits and Systems Society all over the world. And it's a great pleasure for me to give the talk today. So my talk today is on hardware security. I'm going to talk about two different topics. One is how do we encrypt chips before they go to the foundry, so the attackers who are trying to learn about our chips cannot really figure out what the parameters are. So that's kind of one objective. The second goal is how do we authenticate these chips using physical unclonable functions. So those are the two topics I'm going to talk about. So to give a brief background and motivation for the talk today, the so-called design dimensions from decades ago on area, speed, and power and energy consumption have shifted to address reliability and security. There has been a globalization of integrated circuits. People in a company are located in many countries, and the different design teams are writing Verilog code or designing different parts of the chips. They finally get integrated and sent to the foundry. So at any stage of these designs, whether it is some IP provider from some group or the foundry, some disgruntled employee in the foundry, any of these stages, there can be some malfunction of some kind. And that's what we are going to talk about. So lost revenue, think about the company X sent the mask to foundry Y. Now foundry Y sent back the mask to company X, but also provided 10 million chips of the same thing in the black market. So now, well, the company X has lost revenue and lost jobs due to these excess parts. Hardware security is critical to defense. Obfuscation is necessary to prevent anti-counterfeit. So design of integrated circuits that can be authenticated and obfuscated for systems with heterogeneous and complex hierarchies. That's kind of what I'm talking about today. We have been reading about many scenarios where people recycle electronics products, take old parts and sell them as new parts or put them into printed circuit boards. And there has been lot of examples of that. And there is paper from Teranipur and Vyasanor in Spectrum. Okay, so so in the first part of the talk, I will talk about how do we obfuscate or encrypt the designs during the design stage such that we can prevent reverse engineering. So where somebody looks at what the chip contains by looking at it in the powerful microscopes. So we are going to prevent that, even though the attacker or the enemy of the company or the competitor or whoever is trying to learn about the parameters of the product, they can look under the microscope, but they still can't learn the secrets because we are hiding the secrets with the control part of the chip during design stage. Okay, so that can protect key parameters, prevent sale of excess parts. Well, now the foundry can design 10 million extra parts and send it to the black market or underground market, but they don't have the key. We have encrypted the design. So if they don't have the key, they can't sell it to somebody because somebody doesn't know how to make the chip work with the right key. So I'm going to talk about the first paper we wrote. I should say this is kind of a new thing that there has been a lot of work on so-called logic encryption, but I'm not talking about that. I'm talking about encrypting the functionality or functional obfuscation encryption. So I'm going to briefly start with the idea that we published a paper in 2015 on fixed obfuscation, and which I then later on learned that was a great first idea, but then it's easy to attack the circuit. If you have the chip and you have the patience, you can quickly learn the right key. So then that led to this idea of dynamic functional obfuscation, which makes it truly hard in the sense that it can take billions of years to learn the key. So we'll talk about that. In the second part of the talk, I'm going to talk about this small circuits called PUF, physical unclonable functions. And we will quickly see that this MUX PUF that I'm going to talk about, although the name says unclonable, proposed by Srini Devadas at MIT, and people quickly saw that, well, it's not really unclonable, it can be cloned easily, the model can be learned easily. So how can we have truly unclonable functions which are secure and can be used for authentication, and the attacker cannot learn the model easily? So I'm going to talk about that what's written in the red color here, feed forward XOR MUX PUF, and that's a paper we published recently, and that's what I believe is truly unclonable, and we'll get to that. Okay, so those are the two topics. Let me begin with the first topic, the functional obfuscation and encryption of the hardware circuits. Hardware obfuscation is a technique where the structure of the electronic hardware is modified to intentionally conceal its functionality, which makes it significantly more difficult to reverse engineer. Okay, so that's really the notion of hardware obfuscation or encryption. I'm going to talk about really some simple examples from DSP circuits, but any circuit can be encrypted as long as we have a finite state machine or a controller. And what we are trying to do is we are trying to encrypt the circuit using the keys, and by changing the control flow of the system, the data flow or the data path is kept intact. It's only the control flow that's being modified by the key bits. Okay, so the DSP is part of many operations, whether it's wireless, 3G, 4G, 5G, voice over IP, video codec, FIR filter, and so those are some examples. FFTs. So we'll talk about FFTs. So why are we calling it encryption? So if you think about the traditional encryption, where Alice is sending a secure message in an insecure channel to Bob using a secret key. So think about a design house. So the design house is sending the mask to the foundry. The foundry manufactures the chip and sends it back to the design house or a third-party customer company that then sells it to end users. Okay. So now the design house is not really designing the whole thing. There are IP providers from external companies, from internal companies, many different groups within the company at different locations. So think about hundreds of IP vendors, both internal and external, sending their parts to the design house. Design house integrates all of these and then sends the mask to foundry. Now think about each of these hundreds of IP vendors can incorporate a key. Let's say we have 100 IP vendors, each incorporates a 3 or 4 bit key. So now I have a 300 or 400 bit key. The design house then incorporates another, say, 20 bit key. So now we have 420 bit key. And so now that's the key that somebody really, the customer company, needs to know before the chip can be programmed correctly and sent to the end user. Okay, so that's called the encrypting the design during the design process. So what does it mean to have these key bits, and what are the key bits doing to change the functionality? So think about, if I have a chip that's computing certain function in a correct way, that's called the correct functionality. I might have the chip doing many different correct functionalities. For example, I might have an FFT chip that can be configured as 1,000 point FFT, 4,000 point FFT, and 16,000 point FFT. So now I have what I said, 3 meaningful modes, because I want to reconfigure the chip to operate in 3 meaningful ways. So I can have 3 different correct keys that will trigger the 3 meaningful mode. So each key bit corresponding to one meaningful mode. While we have these few meaningful modes, I am creating hundreds and thousands or millions of garbage modes, non-meaningful or garbage modes. That means if the key bit is wrong, it's computing something, but it's computing garbage. And so when the key bit is wrong, for example, I am garbling the control flow of the circuit. So the control signals are generating the that control signals that are garbled, and that means the chip is computing something, but that's computing garbage. And so let me try to see how we can explain that idea of creating garbage control signals if a key bit is wrong. So that's called the fixed. So I'm starting with a very simple idea of fixed obfuscation, where the key bit is correct, control flow is correct, and the chip is computing correctly. So to motivate this idea, let me start with redesigning the FFT chip to incorporate or encrypt this key, encrypt this chip using key bits. So we are incorporating key bits to the FFT chip to secure the FFT. Okay, so the details of that design is in this paper from 2015, and I'm not going to talk about that, but basically think about this is a 16-point FFT example that is log 16 or 4 stages, and there are out of the 4 stages, each stage has 16 inputs, 16 outputs that are computed by 8 butterflies. So 8 butterflies are taking each butterfly taking 2 inputs and computing 2 outputs, and 8 butterflies are folded or time multiplexed in time to a single butterfly in hardware. So you can think of that as a folding or time multiplexing factor of 8. Okay, so in this FFT, there are essentially 2 types of blocks. They call butterfly blocks, butterfly 1 and 2, and there is this delay switch delay. Without getting into details of these building blocks, so if you look at the butterfly block on the right called BF2, butterfly type 2, there is a control bit called T. So that T bit, what does the T bit do? The T bit passes the signal X2, real part and imaginary part, to the right as it is. If the control bit, let's say, is 0, and if it is 1, then it swaps. The real comes down to the bottom output, imaginary goes to the top output. Why are we doing that? Well, in the FFT, sometimes we don't do anything to the X2, but sometimes we multiply by minus J, so the twiddle factor, and then I swap the real and imaginary part. And that's controlled by this control bit T. In the delay switch delay, the inputs to these cross-coupled multiplexers either go straight or are swapped and then go to the right. Okay, so now that control bit is called S. So if you think about this switch here, shown here, this switch control bit S works correctly if the control generated sequence is alternately 0 and 1. So 0, 1, 0, 1, 0, 1, 0, 1, and that computes correctly. Now what happens if I make them all ones or all zeros? Well, then it's computing garbage. Okay, it's computing garbage. Sometimes it's just reordered. Sometimes it's skewed and reordered. I can change them in any way I like. I can make them 001, 001. I can garble them in thousands of ways, or maybe tens of thousands of ways. Okay. In the FFT that I talked about, multiplying by twiddle factor minus J or not multiplying by twiddle factor, then that the control bit T works again correctly in this example. If it is alternately 0, 1, I can make them all zeros. I can make them all ones. If it so happens that if I make them all zeros, then half the outputs are wrong. So half the control bits outputs are wrong. That means the data path is computing wrong things. So it's very easy to garble these control bits in thousands of ways by using some random logic. So in this FFT, I can use the controller. Let me Okay, let me see if I can just go to the controller and then I'll come back to these couple of slides. Yeah, here is the controller. So in the N stage FFT, I have a log n bit counter. I can generate these various counter bits, and from the counter bits, now I'm generating these control signals S and T, but those are now the control signals are now generated by having many inputs to a multiplexer. The multiplexers are controlled by key bits marked here K. We'll come. So that's how I garble these things. Okay, we'll come back to that again. So the obfuscation idea here is, so think about, I have an initialization key. If the key has two parts, initialization key and the mode mapping key or the configure key. If the initialization key is wrong, then you retry after you try few times and still wrong, then you do a denial of service and disconnect everything so the person can't use this device anymore. If the initialization key is correct, then you do this second part of the key, called the configure key, and if that's yes, then it's going to compute the correct design. If it is not correct, it might be computing another mode that I didn't want, or some garbage modes. So that's the whole idea of encrypting the chip. Now it turns out, and we'll get to that, the fixed obfuscation means if the key bit is correct, control bit is correct. If the key bit is wrong, control bit is wrong. That's called fixed obfuscation. Fixed obfuscation can be hacked easily. Okay, so what can we do to really make it harder for the attacker to learn the key? Well, so we can think about, okay, now let's try to encrypt this by using some trigger signals. So we are borrowing some ideas known as hardware trojans. Hardware trojans are creating trigger circuits that go high occasionally, otherwise low. So now we are now using these trigger signals. So the idea is these trigger signals trigger incorrect modes for incorrect keys, but only for a small duration of time. So what does that mean? So that now that means that in the previous one, the key bit wrong, control bit wrong. Now we are saying the key bit may be wrong, but the control bit is still correct if the trigger is not high. The control bit is wrong if the trigger goes high. Why are we doing that? Well, we are saying that, okay, if the key bit is wrong and still the circuit output is correct, we are trying to intentionally mislead the attacker to believe that the attacker has found the key. Because the key bit was wrong, it's still computing correctly. However, when the trigger goes high, then it will compute incorrect control bits. And that's okay. That's certainly better than fixed obfuscation. But that's still not great. Because what we really want is to guarantee that the time to attack should be exponential with respect to the key size. And that's achievable, as we show in this paper in Transactions and Information Forensics and Security. That's achievable by what we call dynamic obfuscation. And now we are saying that, okay, now the trigger signals are not generated predictably, but are generated using a random number generator. So I can no longer predict when the trigger signal will go high. So if I can predict when the trigger signal will go high, that's called time varying obfuscation. If I can't predict because a random number generator is creating the trigger signals, then that's called dynamic obfuscation. So we have encrypted the circuit so that it's dynamically encrypted. So to give you a simple example, the fixed obfuscation here, we have two key bits K0, K1, and marked in light green here. So that's the correct 01 is the correct control key bits to generate correct control. And so that's so this is the correct control, and this is the correct control. And if the key bits are wrong, we take C1 prime, C2 prime. So now if the key bit may be wrong, but now this C1 prime is replaced by some function of C1 and T1. So if the trigger is 0, then it's still going to have C1, which means the control is going to be correct. However, if the trigger goes high, then it's going to be C1 prime and control is wrong. Now I have a dynamic obfuscation where there is a random number generator, and this input to the MUX is now a function of C1, the trigger signal, and the random number generator, and the trigger will go high depending on the status of the random number generator, and that's what we call dynamic obfuscation. Okay, this is showing how the Verilog code of the original control is modified to embed these key bits. I'm not going to go to that. So basically, I can say that, well, the time to attack for a fixed obfuscation using a 100 megahertz clock is 21 seconds. And in this particular example of the, I can now make the time to attack 1 billion years if I use dynamic obfuscation. So the area and power overheads are small because we are not changing the data path. We are only garbling the control signals by using small number of random logic circuits, and that allows the ability to encrypt or obfuscate circuits. Static obfuscation, lower bound on time to attack is 1. Time varying obfuscation, lower bound on time to attack is proportional to number of key bits k. Dynamic obfuscation, lower bound on time to attack is exponential in the number of key bits 2 to the power k. Okay, so that's really the advantage. So that was a very interesting work because it tries to now prevent the foundry from producing excess parts and selling it in black market. It also prevents competing companies to look under microscope because people are trying to learn. Some company may have lost revenue because a competing product is now taking 1/3 energy consumption, and the customer, the competing company might have certain IP, and the company wants to learn the competitor's IP. So now let's say that the competitor is using a 10 tap digital filter, whereas the company is using a 30 tap digital filter, and the company wants to learn why did the power go down 3 times. Well, now the company can't really learn whether it is a 10 tap or a 30 tap filter because we have hidden the functionality of the number of taps in the control circuits using keys. So we have protected some of the key parameters of the design by encrypting the functionality. You can do that hierarchically so that the key bits used at each level are only known to the design house or IP vendor at higher levels. It is unknown to other IP vendors at same level or level below. So that's how not all the 100 engineers contributing to the product, they all don't know, they still don't know what the key bits are. Okay, so I'm going to switch the topic and go to the next part of the topic on multiplexer physical unclonable functions. So the first paper published by Sanani Devadas at MIT, this MUX PUF multiplexer physical unclonable functions. So think about I have a let's say that I have a 100 stage MUX PUF. At each stage I have a control bit. Control bit is 0 or 1. If the control bit is 0, then the signal is propagated straight. If it is 1, it's swapped. Okay. So I can call this 100 challenge bits or 100 control bits together as a challenge, single challenge. And if I pass a rising edge of the clock, it will propagate through, sometimes swap, sometimes straight, and after swapping or going straight, it will eventually reach the arbiter. If the rising edge of the clock reaches the top input of the arbiter, I say the response is 1. If it reaches the bottom input, I say the response is 0. Then if I want to create a 1000-bit signature, I apply 1000 challenges. Each challenge is now 100 bits. I apply 1000 challenges. I have a 1000-bit signature of the chip. Now it turns out that there's enough manufacturing and process variation of the chip that leads to unique signature of the chip, and that's the basic idea. So although these are called unclonable functions, we can easily learn because it's a linear PUF. I can create a linear model, and the linear model can predict the response correctly, and it's really no longer unclonable. It's easily cloned. So if this is showing if this input is control input is 0, then it goes straight. If the control input is 1, path is swapped. Top going to bottom, bottom going to top. So there is an inherent path delay difference between the signal propagating straight or signal swapped. And we are going to call that delay difference of each stage delta I. Delta I is a random variable. Well, after the chip is fabricated, it's no longer random. But before the chip is fabricated, that's a random variable. So that path delay difference can be used to create a total path delay difference called delta of all the n stages. And if the delta is greater than 0, then we say the response signature is 1. If it is less than 0, that's 0. This is a linear model that has this n plus n parameters. I can learn the n parameters by any kind of machine learning model, by linear regression, or by some other model. Okay, so it's no longer unclonable. It can be easily cloned. How can we bring non-linearity? We can bring non-linearity. A simple example of non-linearity is what we call the feed-forward PUF, where the this particular stage here, the MUX stage, is not being controlled by an external bit of the challenge, but I take these two outputs of this arbiter stage and then put them into an internal arbiter. That output is now a challenge bit to this stage. So that's builds some non-linearity. And I can also take that arbiter output and feed that as challenge bits to two consecutive MUX stages. And the advantage of doing that, it really makes it more clonable, more predictable, more reliable. So here it is less predictable, less reliable, more secure. More the reliability and more easily I can predict it, like the linear PUF, very reliable, easily predictable, but insecure or clonable, easily attackable. Now this is somewhere in between the linear model and the feed-forward model. Okay, so so I briefly alluded to the path delay difference of each stage. The path delay difference between the straight path and the swapped path, delta I. If we call this path delay of the straight and swapped as mean mu and variance sigma squared, the path delay difference delta I is the difference of these two. That's going to be 0 mean with variance 2 sigma squared. Okay, so so we can model these PUF responses. We can also create, even though these are non-linear, there is non-linearity. So the model is harder to predict, no longer predictable by a linear model. So I can't use a linear regression, but I can use machine learning models like the neural networks to predict feed forward and modified feed forward. Okay, we'll see some of that. Okay, this is a chip that we fabricated along with my collaborator and colleague, Professor Chris Kim. So what this chip does, so it deviated from the traditional idea of hard PUFs, or what we call hard PUF. The response generated is 0 or 1. So now this is really an example of soft PUF, where the response is not a 0 or 1, but a probability. Okay, what does that mean? So if we apply a challenge bit to the chip has all the control signals to repeat that challenge, let's say 100,000 times. So if I apply the same challenge 100,000 times, let's say that the response is 1 95,000 times. Then I said a probability of 1 is 0.95. If the response is 1 8,000 times, that means the response is likely 0 because it's 0 92,000 times. Probability of 0 is 0.92. So now the advantage of the soft PUF is that I can use a thresholding to throw out the so-called unstable challenges. All challenges are not necessarily stable. What does that mean? Well, it so happens that if I say, okay, well, if the probability of 1 is 90% or higher, then the response is 1. If the probability of 0 is 90% or higher, then the response is 0. In between, I can say, well, this is an unstable challenge. If the probability of 1 is 60,000 out of 100,000, 0.6, then that's not a stable challenge because I'm getting 60,000 times 1, 40,000 times 0. Do not use that challenge for authentication. So there is an interest in understanding what the challenge, stable challenges are. So this is the first PUF chip, and the PUF chip really allowed us to collect a lot of data, and the prior work was all based on simulations. We have data coming out of the lab. The lab data now allows us to verify the independence assumptions, namely the path delay difference of each stage is independent. So in this particular one, we just took a linear model and used a least mean squared adaptive filter algorithm to learn these n parameters, the path delay differences. So there is 32, this was a 32 stage PUF. So there are 33 parameters, so the 32 stage delay differences and the delay of the arbiter. So 33 models can be predicted, and we showed that the LMS learns the correct parameters, then the correct parameters can clone that PUF. Okay, so we also showed that the path delay differences of all the stages across, there were 96 chips, PUF chips in the chip, and from chip to chip or PUF to PUF and stage to stage, all those delay differences were truly independent after fabrication, and I can predict for hard and soft responses. I can create models. I'm going to skip quickly over some of these slides. Essentially, I can create models whether based on simple perceptrons or based on neural network models to predict both hard as well as soft responses. So I'm not going to, let me just skip a few of the slides. But for example, multi-layer perceptron with one hidden layer can be used for feed-forward PUF for the hard response. For a soft response, I need 2 hidden layers of the multi-layer perceptron, 30 neurons in layer 1, 10 neurons in layer 2. So we can, so at the end of the day, even though there are non-linearities, we can still predict these kinds of things. Okay, so what then can we do to make these unpredictable? Well, the exclusive OR is a nonlinear function, and there have been prior work on XOR PUF. So we took this data out of the chip that we had fabricated, and in this paper with my colleague in 2017 DAC. So here we showed that so there are 96 PUFs in each chip, and we had many chips fabricated, something like 20 or 25 chips. So the idea now is, okay, so now let's take n PUFs, independent PUFs, and apply the same challenge to all of these, and then we get n responses, take the exclusive OR of all of these, and that's our final response. Okay, that's certainly a lot more nonlinear compared to the feed-forward nonlinearity that I described, and that becomes harder to predict, harder to create model. And indeed, so the chip that we had fabricated, the probability that we can get a stable 1. So probability of stable 1 is 40%. Probability of stable 0 is almost 40%. So applying 1 million random challenges, we can see that the probability that we will get a stable 1 or 0 is 80%, and the remaining 20%, the challenge is unstable. Okay, so 80% challenge response pairs are stable. And now we are plotting this for various exclusive OR sizes, 4 independent PUFs, then exclusive OR all the way up to 10 exclusive OR PUFs, 10 PUFs, and then take the exclusive OR. By using machine learning model, we can see that with 4, 5, 6, well, we can still predict this quickly with prediction accuracy of almost 100%, although the number of training samples increases. However, with a 10, I see that it's now gone down from 100% to 86% for if I have more than 10 PUFs, and then that will become more secure. What I really want is the prediction accuracy to be about 50%. That's like flipping a coin. So you can't predict it. The machine learning model cannot predict it. That's called a secure or unpredictable attack resistant PUF. Okay, so okay, then so there is one other parameter, the number of stable challenge response pairs goes down exponentially as we take more and more XOR PUFs. Okay, so if I take, remember that 80% of the challenges were stable for one PUF. If I take 10 components and take exclusive OR, the number of stable challenge response pairs is now 0.8 raised to the power 10. So goes down exponentially. Okay, so so let me go to the last part of the talk, which is feed forward XOR PUF. Okay, so now we are saying, okay, so how can we, by the way, I should say that so the XOR PUF was definitely a lot more secure and was, although the number of stable challenge response pairs went down, but there was this Baker attack where Baker showed that the exclusive OR PUFs can be attacked. The model can be learned. Okay, so the XOR PUF can be learned, although more secure, but still can be learned by so-called Baker attack. And then, okay, so now let's take back our idea of the components being, so the XOR PUF has multiple components. Each component is still linear, but now let's have each component is non-linear by feed-forward XOR PUF. And finally, I will argue that the XOR PUF components are not only non-linear but heterogeneous. Their non-linearity is not identical. Okay, so so then we are trying to design PUFs that cannot be attacked. Model cannot be learned. Okay, so if a feed-forward XOR PUFs, they are more attack resistant. They cannot be accurately modeled if the number of components is more than 5. So if the number of components of the feed-forward PUF is more than 5, as we see here, then the accuracy is 50%. That means they cannot be easily learned. Okay, so there is more to soft response thresholding, but let me try to describe these last couple of slides. So this slide here is showing the various configurations here. So we are showing here, so this number here 4/8, that means there are 4 internal arbiters, okay, and 8 different feed forward loops. So the loops are, I showed the modified feed forward, and so by using different components, so the feed forward loops here, so each component here has different configurations, and by having these so-called modified feed forward, I can make sure that these feed forward PUFs are attack resistant. When these are attack resistant, they're inherently unreliable. So how do we handle the unreliability part? the way we handle the unreliability part is we have ways to find out what the stable challenges are. And if I can, it is true that if I had 100-stage PUF, the total number of challenges is 2 to the power 100. A very small fraction of that, let's say just 2% of that, is now stable, but that's still a big number. So I can have a very small percent of a large number of challenge response pairs. So, so the reliability can be increased to large numbers by a variety of techniques, by using the modified feed forward, where the same internal arbiter goes to multiple stages. The 8 or 10 different components of the XOR PUF are not identical. So by heterogeneity and by feed forward, we are able to create XOR PUFs that are secure and attack resistant and reliable. So this paper in TIFS is published already, and it shows that the feed forward XOR PUFs cannot be accurately modeled if the number of component PUFs is more than 5. Reliability decreases as more components are used. However, I can increase the reliability by using modified feed forward loops, and can be increased by thresholding soft responses that I briefly talked about. And the heterogeneity makes it more secure. Heterogeneous, each component of the XOR PUF is not same as other components. Okay, so so that brings me to the end of the talk. Control flow modifications can obfuscate circuits to design chips that are harder to reverse engineer. Key-based obfuscation can render excess parts unusable. Linear and nonlinear PUFs can be modeled easily. XOR PUFs can be secure and reliable at the same time. New PUF circuits that are attack resistant can yet, there is also a significant opportunity to do new research as well. So this work was supported by the National Science Foundation and Semiconductor Research Corporation, and we are certainly grateful to the industrial liaisons that provided numerous inputs. Let me just acknowledge a number of students. Dr. Kim, my colleague at the university, Ingji Lau, worked on the project, is now professor at assistant professor at Clemson. Sandhya Koteshwara did a lot of the work. She's at IBM T.J. Watson Research Center. Sandeep Avaru continuing his PhD. Chen Zhao at Maxim, and Anup Koili at Qualcomm. So many students and many other students that did other parts that I didn't talk about. Okay, so thank you very much for listening to my talk. I will be, I can take any questions from the audience. Well, Ricardo, are you going to see if there are questions?
So thank you very much, Professor Parhi. I touched the wrong button here, sorry. So I have a question of Matheus Leme. So thank you very much for the presentation, Professor Parhi. On which platform does sequentially triggered mode-based design was implemented? Did you arrive to evaluate security using side channel attacks for all these proposed solutions?
Okay, those are good questions. So first of all, the Verilog code that we wrote here was resynthesized using 65 nanometer technology for ASIC design. So that was the platform that we used. The second question is about side channel attack resistance of these circuits. No, we did not explore. We did not explore the side channel attack resistance. I mean, that is really a topic of future research. I think I can see there is potential future research to take these dynamically functionally encrypted circuits and see if the side channel attack can be used to learn the key and the functionality. So we didn't work on that, but that's a topic of future research.
Thank you very much. So another question by Xing Shen from Arizona State University. Does obfuscation introduce time delay?
That is yes, that is a good question. So we are obfuscating these circuits by embedding some control flow. Definitely, it is possible that there will be some time delay. So I expect that it is possible. I mean, I guess let's talk about where is the bottleneck. If the bottleneck is the control flow, then we have increased the critical path of the control flow by introducing additional multiplexers. So that's kind of where the critical path bottleneck is coming in. It's not coming in the data path, but it's coming in the control flow path. So yes, if the control flow was the critical path bottleneck, now that's going to be increased by these multiplexer critical paths. So yes, so I mean there is definitely that overhead.
Okay, thank you. So I have also one question. Before that, some comments. So one of the works we are doing are related to the reduction of the transistor count. And then to do that, we needed to do logical optimization in order to be able to go deeply in the logical minimization. And for that, development of tools to do the automatic layout of any transistor network. Then we are able to do any layout we want automatically. So doing this, we observed some time ago that also could be interesting also to improve security, because we can do different layouts for the same function. So what is your opinion or consideration about this possibility to have different layouts for the same function in order to complicate the life of reverse engineering?
Yeah, so I think what you are saying is I can create different layouts, but I mean eventually once I have to map the key bits to the layout. So so the layout, so in that case, I have to have multiple instances. So multiple layout instances have to fit into the chip. And then those instances have to be controlled by the key. So I could potentially build in some encryption using multiple layouts, and I'm not sure what the goal is. The goal, because now I have to increase the area. I have to increase, well, not exactly double, maybe approximately double the area, because I have to put those into the chip.
So yes, there is another one by Julio Lozano. Are XOR PUFs power hungry? If so, is there a low power consumption alternative?
That is a good question. So the question is, are XOR PUFs power hungry? Well, yes, I mean, absolutely taking more power than the ordinary one component PUF, and yes, because we have n components in hardware, so we are increasing the energy consumption by n times. Uh, Absolutely. But think about, we authenticate the device only a few times. I mean, the device is doing its computations, but let's say we are authenticating it every few times a day or few times a month or whatever. So the fact that the authentication is activated irregularly and infrequently, the power and energy overhead, I don't think is the major, although true, it's not a big bottleneck because the goal is really to achieve attack resistance while not sacrificing reliability in authentication. So that's why even though there is n times increase in the energy consumption, that's not a big barrier.
So thank you very much again, Professor Parhi. Thank you to everybody that attended this very nice talk done today. Thank you very much. Bye-bye. See you next
Bye bye.
Wednesday and Friday.
Thank you. Bye bye.